Close your eyes. Let the tension leave your shoulders. Let your breathing slow. Let your body sink a little deeper into the warmth of wherever you are resting tonight, and allow your mind to travel somewhere far, far away. Not to another country, not to another continent, but to another place entirely. A place so distant and so strange that the very laws of physics behave differently there. A place where the fundamental forces that hold your body together, that hold atoms together, that hold reality together as you understand it, are pushed to limits that should not be possible. Tonight, we are going to visit the most terrifying stars in the universe, and we are going to do it gently, slowly, one idea at a time, so that by the time we arrive, you may already be drifting into sleep. Imagine, for a moment, that you are floating in space. You are somewhere deep in the Milky Way galaxy, far from Earth, far from the sun, surrounded on all sides by the cold, silent vastness of the cosmos. There are stars in every direction, some bright and close, others dim and impossibly distant, scattered across the blackness like grains of luminous sand. You feel nothing. There is no wind, no sound, no sensation of temperature. You are simply there, suspended in the void, weightless and still. It is peaceful. It is quiet. It is the kind of quiet that goes beyond the absence of sound, a quiet that seems to have texture and depth, as though silence itself were a substance that fills the spaces between the stars. And then something changes. You feel it before you understand it. A sensation in your body, subtle at first, like a faint pulling. A gentle tug in every cell, in every molecule. It is not painful, not yet, but it is unmistakable. Something is reaching across the emptiness of space and touching you. Not with hands, not with light, not with gravity in the way you understand it, but with a force so immense, so utterly beyond anything you have ever experienced, that your body begins to respond in ways that make no sense. The iron in your blood, those tiny atoms of iron that your red blood cells carry through your veins, begins to shift. You can feel it, or rather, you can feel the effect of it, a strange warmth, a pulling, as though some invisible hand were trying to rearrange the very atoms inside you. Your hair stands on end, though there is no static electricity here. Every nerve in your body seems to hum with a frequency you cannot hear, but can somehow feel, deep in your bones, deep in the marrow of your bones. You turn your head, slowly, searching for the source of this impossible force, and there, in the distance, you see it. It is small, impossibly, almost absurdly small, a sphere no wider than a city, perhaps 20 kilometers across, hanging in the blackness of space like a glowing marble. It does not look terrifying. It does not look like the most dangerous object in the known universe. It looks, if anything, almost ordinary, a tiny point of light in a galaxy full of much larger and more dramatic objects. But what you are feeling in your body, that pulling, that rearranging, that hum in your blood and your bones, is coming from that small, quiet sphere. And you are thousands of light years away from it. What you are looking at is a magnetar, Magnetar. And it is, by almost any measure, the most extreme, the most violent, the most powerful, and the most terrifying type of star in the entire known universe. Not because of its size, which is tiny by stellar standards. Not because of its temperature, though its surface is extraordinarily hot. Not because of its gravity, though its gravitational pull is immense. A magnetar is terrifying because of its magnetic field, a magnetic field so overwhelmingly, incomprehensibly powerful that it warps the fabric of space, distorts the shape of atoms, splits light into strange new configurations, and can kill you from a distance that, on a cosmic scale, is almost unimaginably far away. A magnetar's magnetic field is roughly 1 quadrillion times stronger than the magnetic field of the Earth. 1 quadrillion. That is a 1 followed by 15 zeros. It is a number so large that writing it out would fill this sentence, and yet it only begins to describe the difference between the gentle magnetic field that guides your compass needle and the annihilating force that surrounds a magnetar. Let us put that number in perspective, because numbers this large have a tendency to wash over us without leaving any real impression. The Earth has a magnetic field. You know this. It is what makes compasses work, what protects us from the worst of the solar wind, what creates the shimmering auroras near the poles. The strength of Earth's magnetic field at the surface is roughly half a gauss. A gauss is a unit of magnetic field strength, and half a gauss is extraordinarily feeble by cosmic standards. A refrigerator magnet, the kind you use to hold a shopping list to your refrigerator door, has a magnetic field of about 100 gauss. A medical MRI machine, the kind that can peer inside your body and produce detailed images of your organs and tissues, generates a magnetic field of roughly 30,000 gauss, and it requires careful safety protocols because, at that strength, the magnetic field can pull metal objects across the room. An MRI technician will ask you to remove all jewelry, all metal, anything ferromagnetic before you enter the scanning room because at 30,000 gauss, loose metal becomes a projectile. A magnetar has a magnetic field of approximately 1 quadrillion gauss. That is 10 to the power of 15 gauss. It is roughly 30 billion times stronger than the most powerful MRI machine on Earth. 30 billion times. If an MRI machine's field can pull a set of keys across a room, a magnetar's field can restructure the electrons inside an atom from thousands of kilometers away. It is not merely a stronger version of the magnetic fields we know. It is something qualitatively different, a force so extreme that it changes the rules of physics, that it takes the familiar world of electromagnetism and pushes it into a regime where quantum mechanics and relativity and the deepest laws of nature all begin to behave in ways that were only theorized on chalkboards and in equations, before we discovered that magnetars actually exist. A magnetar is a type of neutron, new-tron star. A neutron star is what remains after a massive star dies in a catastrophic explosion called a supernova. So aioi per novuh. We will explore how neutron stars are born in great detail in the next section, but for now, let us simply establish what we are dealing with. A neutron star is an object roughly 20 kilometers in diameter, about the size of a medium city, that contains more mass than our entire sun. It is composed almost entirely of neutrons, the subatomic particles that, along with protons, make up the nuclei of atoms. In a neutron star, these neutrons are packed so tightly together that a single teaspoon of neutron star material would weigh roughly 4 billion tons. 4 billion tons in a teaspoon. It is a density so extreme that it defies every intuition we have about the physical world. If you could somehow scoop up a teaspoon of a neutron star and place it on the surface of the Earth, it would weigh more than every building, every vehicle, every mountain, every ocean of water on the entire planet, all compressed into a volume smaller than a sugar cube. Most neutron stars are already extraordinary objects. They spin at incredible rates, some completing hundreds of rotations per second. They have gravitational fields so intense that light itself is bent as it passes near their surface. They are, by almost any measure, among the most extreme objects in the known universe. But a magnetar is a neutron star that has gone further, that has acquired a magnetic field so powerful that it elevates the neutron star from merely extraordinary to genuinely terrifying. Not all neutron stars are magnetars. In fact, only a small fraction, roughly 1 in 10, are believed to become magnetars. The rest are ordinary neutron stars, or pulsars, pulsars, or other varieties. But the ones that do become magnetars are, without exaggeration, the most powerfully magnetized objects in the entire observable universe. Nothing else comes close. Not the magnetic fields of other stars, not the fields generated by the most powerful magnets in our laboratories, not even the fields found near black holes. A magnetar stands alone at the extreme end of the electromagnetic spectrum, a monument to what happens when nature pushes a fundamental force to its absolute limit. The word magnetar itself is a portmanteau, a combination of the words magnetic and star. It was coined in the early 1990s by the theoretical astrophysicists Robert Duncan and Christopher Thompson, who first developed the comprehensive theory explaining these objects. Before their work, the phenomena that we now attribute to magnetars were deeply puzzling to astronomers. Strange bursts of gamma rays, anomalous X-ray emissions from isolated neutron stars, behaviors that did not fit any existing model. Duncan and Thomson proposed that all of these puzzles could be solved by a single idea. A neutron star with a magnetic field 1,000 times stronger than any previously considered. Their proposal was bold, almost audacious. At the time, many of their colleagues were skeptical. A magnetic field of 10 to the 15th Gauss seemed fantastical, an extrapolation so far beyond the known that it bordered on speculation. But as the years passed and the observational evidence accumulated, the Magnetar model was vindicated again and again by data that fit no other explanation. Today, the Magnetar is an established class of astrophysical object, recognized by astronomers around the world, and the subject of hundreds of scientific papers each year. It is worth pausing to appreciate the scale of what we are discussing, because the human mind has a natural tendency to absorb large numbers without truly processing them. When we say that a magnetar's magnetic field is 1 quadrillion times stronger than Earth's, the number slides past us, impressive in the abstract but difficult to feel. So let us try a different approach. Imagine that you are standing in a field on a clear night, holding a compass. The compass needle swings gently to the north, responding to Earth's magnetic field, a field so faint that you cannot feel it with your body, cannot see it, cannot hear it. It is there, but it is so weak that only a magnetized needle, free to rotate, can detect it. Now imagine that the magnetic field around you begins to grow stronger. At 100 times Earth's field, you would notice nothing different. At 1,000 times, still nothing perceptible to your body. At 1,000,000 times, roughly the strength of a strong laboratory magnet, you might begin to feel a strange tingling if you were wearing metal jewelry, and any loose iron objects would fly toward the strongest part of the field. At 1,000,000,000 times Earth's field, the field would be strong enough to affect the water molecules in your body, though the effect would still be subtle. At 1,000,000,000,000 times, roughly the field of an ordinary neutron star, the field would begin to distort the electron orbitals in the atoms of your body, and the forces on the iron in your blood would become significant. And at 1 quadrillion times the field of a magnetar, every atom in your body would be restructured, every molecule rearranged, every chemical bond altered. You would cease to exist as a biological organism. You would cease to exist as a recognizable arrangement of matter. The field would reduce you to a thin strand of elongated atoms aligned along the magnetic field direction. A tragic, microscopic monument to the frailty of biology in the face of fundamental forces. The history of our understanding of magnetars is, in many ways, a parable about the relationship between theory and observation in science. The theoretical prediction came first. In 1934, just 2 years after the discovery of the neutron by James Chadwick at the Cavendish Laboratory in Cambridge, two astronomers named Walter Baade, B-A-H Duh, and Fritz Zwicky, Z-Y-K-E, proposed that neutron stars might exist. Working at the Mount Wilson Observatory in California, Baade and Zwicky suggested that in the aftermath of a supernova explosion, the core of the star might collapse to form a compact object composed entirely of neutrons, an object of incredible density and small size. Their prediction was prescient but ahead of its time. Neutron stars remained theoretical constructs for over 3 decades, until the discovery of pulsars in 1967 provided the first observational evidence that they were real. And then it would take another quarter-century before Duncan and Thomson proposed the Magnetar, extending the neutron star concept into a regime of magnetic field strength that pushed the boundaries of what anyone thought was physically possible. If you enjoy falling asleep to these journeys through the cosmos, consider subscribing to the Science Pillow. Every week, a new documentary arrives, designed to carry you gently through the wonders of the universe and into a peaceful sleep. All you need to do is press the subscribe button, and the stars will be waiting for you every night. You do not need to stay awake. You do not need to take notes. Just lie back, close your eyes, and let the universe do the rest. The story of Magnetars is a story that stretches across the entire history of stellar physics, from the first tentative predictions of neutron stars in the 1930s to the dramatic observations that confirmed magnetars as a distinct class of objects in the 1990s and beyond. It is a story of theoretical physicists who imagined objects so extreme that many of their colleagues thought they were fantasies, and of observational astronomers who detected bursts of energy so powerful that they had no explanation for them, until they realized that the fantasies were real. It is a story about the death of giant stars, the birth of impossible objects, the behavior of matter under conditions that cannot be replicated in any laboratory on Earth, and the violent, beautiful, terrifying consequences of magnetic fields pushed to the breaking point of known physics. Tonight, we are going to tell that story from beginning to end. We will start with the deaths of massive stars, the supernova explosions that forge neutron stars from the collapsing cores of stellar giants. We will explore how, in rare and special circumstances, the newly born neutron star generates a magnetic field 1,000 times stronger than any ordinary neutron star, transforming it into a magnetar. We will examine the properties of that magnetic field in detail, understanding what it does to matter, to light, to the vacuum of space itself. We will witness the violent outbursts that magnetars produce, the starquakes and giant flares that release more energy in a fraction of a second than our sun produces in hundreds of thousands of years. And we will follow the magnetar through its brief, brilliant life, watching as its extraordinary field slowly decays over thousands of years until it fades into the vast population of quiet, ordinary neutron stars that drift silently through the galaxy, their days of fury long behind them. It is a journey through some of the most extreme physics in the universe, but we will take it slowly, one step at a time, and you are welcome to drift off at any point along the way. The universe will still be here tomorrow night, and so will the Magnetars, spinning silently in the dark, their tremendous fields stretching out across the void like invisible sculptures made of pure force. They do not know you are listening. They do not know that on a small blue planet orbiting an ordinary yellow star in an unremarkable spiral arm of the Milky Way, someone is lying in a quiet room, eyes closed, breathing slowly, learning about the most powerful magnets in creation as they gently fall asleep. But there is something beautiful in that, something that connects the vastness of the cosmos to the smallness of this moment. The warmth of your blanket, the softness of your pillow, the quiet rhythm of your breathing. The Magnetars are out there, and you are here. And tonight, for a little while, we will bring those two worlds together. Let us begin with the death of a giant star. Section 2. The death of a giant. Every magnetar begins its existence in the most violent event that the universe regularly produces, the death of a massive star. Not a star like our Sun, which will end its life relatively quietly, swelling into a red giant, shedding its outer layers into a beautiful planetary nebula, and leaving behind a small, dense remnant called a white dwarf. No. The stars that give birth to magnetars are monsters, stellar titans with masses 20, 30, 40, or even 50 times the mass of the Sun. These are the blue supergiants and the red supergiants, the Wolf Rayet, Wolf-Ray AY stars, and the luminous blue variables, the rarest and most spectacular stars in the galaxy. They burn with a ferocity that dwarfs our Sun, pouring out energy at rates millions or even billions of times greater. They are the lighthouses of the galaxy, visible across vast distances, their brilliance marking them as something exceptional, something extraordinary, something that will not last. The life of a massive star is, by stellar standards, breathtakingly short. Our Sun has been burning steadily for roughly 4.5 billion years, and will continue to do so for another 5 billion, a total lifespan of roughly 10 billion years. A massive star with 30 times the Sun's mass might live for only 5 or 6 million years. Some of the most massive stars known, those approaching 100 solar masses, have lifespans measured in just 2 or 3 million years. To put this in perspective, if the Sun's life were compressed into a single calendar year, a massive star's entire existence, from birth to death, would occupy less than a single day. They live fast, they burn bright, and they die young. And when they die, they do not go quietly. The reason massive stars live such short lives is paradoxical and beautiful. You might expect that a star with more fuel, more hydrogen to burn, would last longer. But the opposite is true. Massive stars are so much hotter and denser in their cores that they burn through their fuel at a vastly accelerated rate. The rate of nuclear fusion in a star's core depends not just on the amount of fuel available, but on the temperature and pressure at the center, and both of these increase dramatically with mass. A star with 30 solar masses does not burn its fuel 30 times faster than the Sun. It burns it roughly 30,000 times faster. It is as though the star, knowing somehow that it will not last, decides to live as extravagantly as possible, burning through its inheritance in a blaze of prodigious energy, a stellar aristocrat spending its fortune in a single, magnificent, doomed party. Let us follow a massive star through its life, from birth to death, because the death is what matters for our story, and the death can only be understood in the context of what came before. A massive star is born, like all stars, from the gravitational collapse of a dense region within a molecular cloud. The cloud fragments, the fragment contracts, the core heats up, and when the temperature at the center reaches roughly 10 million Kelvin, nuclear fusion ignites. Hydrogen atoms, or more precisely, hydrogen nuclei, which are just individual protons, begin to fuse together to form helium. This is the same process that powers our Sun, and it is the process that powers every star on the main sequence, the long, stable phase of a star's life during which hydrogen is converted to helium in the core. For a massive star, this phase lasts a few million years. For our Sun, it lasts 10 billion. But the physics is the same. 4 hydrogen nuclei combine, through a series of intermediate steps, to produce 1 helium nucleus plus energy. The energy is released because the helium nucleus has slightly less mass than the 4 hydrogen nuclei that formed it, and that missing mass has been converted into energy according to Einstein's famous equation, E equals mc squared. The energy radiates outward from the core, providing the pressure that supports the star against its own gravity. As long as fusion continues, the star is in balance. Gravity pulls inward. Radiation pressure pushes outward. The star holds. But hydrogen does not last forever. Eventually, the core exhausts its supply of hydrogen, converting all of it into helium. In a low-mass star like the Sun, this triggers a relatively gentle transition. The core contracts, the outer layers expand, and the star becomes a red giant. But in a massive star, the transition is more dramatic and more consequential. When the hydrogen in the core runs out, the core contracts and heats up, because without the outward pressure of hydrogen fusion, gravity begins to squeeze the core more tightly. The temperature rises, and when the core temperature reaches roughly 100 million Kelvin, something remarkable happens. The helium nuclei that were the ash of hydrogen burning become the fuel for a new round of fusion. Helium nuclei begin to fuse together to form carbon through a process called the triple alpha process, because helium nuclei are also known as alpha particles. 3 helium nuclei combine to form 1 carbon nucleus, and energy is released. The star has found a new source of fuel, a new way to hold itself up against gravity. Helium burning in the core provides the pressure that prevents further collapse. This pattern, this sequence of burning one element and then moving on to the next, is the defining story of a massive star's life. Each fuel lasts for a shorter time than the one before, because each successive fusion reaction produces less energy per reaction and requires higher temperatures and pressures to proceed. After helium burning produces a core of carbon, the core contracts again, the temperature rises again, and carbon begins to fuse. Carbon fusion produces neon and magnesium, and it requires temperatures of roughly 600 million Kelvin. Carbon burning in a massive star lasts perhaps 1,000 years. After carbon comes neon burning at roughly 1.2 billion Kelvin. The neon nuclei are photodisintegrated, FOH disintegrated, broken apart by high-energy photons, and the released particles are captured by other neon nuclei to form oxygen and magnesium. Neon burning lasts perhaps a few years. After neon comes oxygen burning at roughly 1.5 billion Kelvin. Oxygen nuclei fuse to form silicon, sulfur, and phosphorus. Oxygen burning lasts perhaps a year or two. And after oxygen comes silicon burning, the final stage, at temperatures approaching 3 billion Kelvin. Silicon nuclei fuse through a complex web of reactions to produce iron and nickel, the most stable elements in nature, the elements with the highest nuclear binding energy per nucleon. Let us pause here and consider what has happened. The star, over the course of its life, has built up an onion-like structure in its interior. At the very center is a core of iron and nickel, the product of silicon burning. Surrounding that core is a shell of silicon and sulfur, the product of oxygen burning. Surrounding that is a shell of oxygen and magnesium, the product of neon burning. Then, a shell of neon and magnesium from carbon burning. Then, a shell of carbon and oxygen from helium burning. And finally, the outermost layers, still composed largely of hydrogen and helium, the original material of the star. Each layer is thinner and hotter than the one above it, and each represents a different chapter in the star's nuclear history. It is a beautiful structure, a kind of geological record written not in rock but in elements, each layer a testament to the fires that burned at the star's center during a different epoch of its life. But the iron core at the center of this onion is a death sentence, and this is why. Every previous stage of nuclear fusion, from hydrogen to helium to carbon to neon to oxygen to silicon, released energy. That energy was carried outward by radiation and convection, providing the pressure that supported the star against its own gravity. But iron is different. Iron sits at the peak of the nuclear binding energy curve. This means that fusing iron nuclei into heavier elements does not release energy. It requires energy. It is an endothermic reaction rather than an exothermic one. For every previous element, fusion was like rolling a ball downhill. The reaction released energy naturally and spontaneously. For iron, fusion is like trying to push a ball uphill. It takes more energy than it gives back. The star has reached the end of the line. There is no more fuel. There is no more energy to be extracted from nuclear fusion. The iron core, growing heavier by the moment as silicon burning continues in the shell above it, sits at the center of the star like a ticking bomb, supported only by the quantum mechanical pressure of electrons being squeezed into an ever smaller space. This pressure is called electron degeneracy, D-gen-UC pressure. It is not a thermal pressure, not caused by the heat and motion of particles. It is a purely quantum mechanical effect, a consequence of the Pauli exclusion principle, which states that no two electrons can occupy the same quantum state simultaneously. As the iron core is compressed by gravity, the electrons are forced into higher and higher energy states, and this creates an outward pressure that resists further compression. It is the same pressure that supports white dwarf stars, the remnants of lower mass stars like our Sun. For a time, electron degeneracy pressure holds the iron core up, preventing it from collapsing further. But there is a limit. In 1930, a young Indian astrophysicist named Subrahmanyan Chandrasekhar, working aboard a steamship traveling from India to England, calculated that electron degeneracy pressure could only support a stellar core up to a certain mass, roughly 1.4 times the mass of the Sun. Beyond that mass, which we now call the Chandrasekhar limit, not even the quantum mechanical pressure of electrons can withstand the force of gravity. The electrons, squeezed beyond their limit, are forced into the protons in the nuclei, combining with them to form neutrons and releasing neutrinos, in the process. This is called electron capture, or inverse beta decay, and it is the beginning of the end. When the iron core of a massive star exceeds the Chandrasekhar limit, the catastrophe is sudden and almost unimaginably violent. The electron degeneracy pressure that was holding the core up vanishes as electrons are absorbed into protons. The core, which a moment ago was roughly the size of the Earth, about 12,000 kilometers in diameter, begins to collapse. And it does not collapse slowly. It collapses at a significant fraction of the speed of light. In less than a second, less than a single heartbeat, the core goes from the size of the Earth to a sphere roughly 20 kilometers across. Think about that. 12,000 kilometers compressed to 20 kilometers. An object the size of a planet compressed to the size of a city. In less than 1 second. The material at the edge of the core is falling inward at velocities approaching 70,000 kilometers per second, roughly a quarter of the speed of light. The collapse is halted, violently and abruptly, when the core reaches nuclear density, the density at which neutrons are packed together as tightly as they are inside an atomic nucleus. At this density, roughly 2.3 times 10 to the 17th kilograms per cubic meter, a new quantum mechanical pressure kicks in, the pressure of neutrons being squeezed together, called neutron degeneracy pressure. Combined with the repulsive component of the strong nuclear force at very short distances, this pressure halts the collapse. The core rebounds. It bounces. Like a rubber ball thrown against a concrete floor, the core of the star, now composed almost entirely of neutrons, bounces back outward. This bounce sends a shock wave racing outward through the infalling material of the star. The shock wave is immensely powerful, carrying an energy that is difficult to comprehend. But initially, the shock wave stalls. As it plows through the dense layers of silicon, oxygen, neon, carbon, and helium that are still falling inward, it loses energy. It collides with infalling material and decelerates. For a few hundred milliseconds, a fraction of a second that determines the fate of the entire star, the shock wave hovers, neither advancing nor retreating, in what astronomers call the stalled shock phase. What revives the shock is one of the most extraordinary phenomena in all of physics. During the collapse of the core, an immense number of neutrinos were produced, roughly 10 to the 58th neutrinos, a number so staggeringly large that it exceeds the number of atoms in 1,000 Earths. These neutrinos carry away roughly 99% of the total gravitational energy released in the collapse, an energy of approximately 3 times 10 to the 46th joules, or about 3 times 10 to the 53 ergs. That is more energy than the Sun will produce in its entire 10 billion year lifetime, released in a burst lasting just a few seconds. Most of these neutrinos stream outward through the star and into space without interacting with anything, because neutrinos are famously reluctant to interact with matter. A neutrino can pass through a wall of solid lead, a light year thick with only a 50-50 chance of being absorbed. But in the extraordinarily dense environment just above the newly formed neutron star core, even neutrinos interact a little. A tiny fraction of them, perhaps 5%, deposit their energy into the material just behind the stalled shock wave. And that tiny fraction of an enormous total is enough. The energy deposited by the neutrinos revives the shock wave, pushing it outward with renewed force. The shock wave accelerates, plowing through the remaining layers of the star, heating them to billions of degrees, triggering new waves of nuclear reactions and, ultimately, blasting the entire outer envelope of the star into space at velocities of thousands of kilometers per second. This is a core collapse supernova, so O per no VUE. It is one of the most energetic events in the universe, outshone only by gamma-ray bursts and certain rare types of superluminous supernovae. For a few weeks, a single supernova can outshine an entire galaxy of 100 billion stars. It produces a rapidly expanding shell of gas and debris called a supernova remnant, which will continue to expand and glow for thousands of years. It creates and disperses heavy elements into the interstellar medium, the elements forged in the star's interior and in the supernova explosion itself. Elements like gold, platinum, uranium, and many of the atoms that make up your body. And at the center of the explosion, where the core once was, it leaves behind a small, dense, rapidly spinning remnant. A sphere of neutrons 20 kilometers across, weighing more than the Sun. A neutron star. This is what remains. 20 kilometers in diameter. 1.5 to 2 solar masses. A density so extreme that a sugar cube-sized piece would weigh as much as all of humanity. A surface gravity roughly 200 billion times the surface gravity of Earth. An escape velocity of roughly 100,000 kilometers per second, 1/3 the speed of light. A surface temperature of roughly 600,000 Kelvin, gradually cooling over millions of years. A spin rate that can be extraordinarily fast, some newly born neutron stars completing dozens or even hundreds of rotations every second, their rotation powered by the conservation of angular momentum during the collapse, the same principle that makes an ice skater spin faster when she pulls her arms in. The star that was once millions of kilometers across has been compressed to 20 kilometers, and its rotation rate has increased proportionally, from a leisurely once every few weeks to a dizzying hundreds of times per second. The interior of a neutron star is one of the most exotic environments in the known universe. The outer layer is a thin crust, perhaps a kilometer thick, composed of iron nuclei arranged in a crystalline lattice, forming a solid surface that is unimaginably harder and more rigid than any material on Earth. Below the crust is the outer core, a fluid of almost pure neutrons. A superfluid, in fact, flowing without friction or viscosity. Deeper still is the inner core, where the density exceeds that of normal nuclear matter, and the exact nature of the material is unknown. Some physicists believe the inner core may contain exotic forms of matter, such as hyperons, Hy-perons, kaon, Ki-on, condensates, or even quark, K-wark matter. A state in which the quarks that make up neutrons and protons are no longer confined inside individual particles, but flow freely in a quark-gluon, GluU-on plasma. We do not know for certain. The conditions in the inner core of a neutron star are so extreme that they cannot be replicated in any laboratory on Earth, and our theoretical understanding of matter at these densities remains incomplete. Many neutron stars are pulsars. A pulsar is a neutron star that emits beams of electromagnetic radiation from its magnetic poles. Radiation that sweeps around as the star rotates, like the beam of a lighthouse. If the Earth happens to lie in the path of one of these beams, we detect a regular pulse of radiation, a pulse that repeats with extraordinary precision, often more precisely than any human-made clock. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell, then a graduate student at Cambridge University, working under the supervision of Anthony Hewish, H.I.O.H.ish. She detected a regular series of radio pulses coming from a fixed point in the sky, repeating every 1.337 seconds with a precision that initially led the research team to wonder, half-jokingly, whether they had detected a signal from an extraterrestrial civilization. They labeled the source LGM-1 for Little Green Men, before it became clear that the signal was coming from a rapidly rotating neutron star. Bell Burnell's discovery was one of the most important in 20th century astrophysics, and it opened the door to the study of neutron stars as observable, detectable objects rather than purely theoretical constructs. A typical pulsar has a magnetic field of roughly 10 to the 12th Gauss, or about 1 trillion Gauss. This is already an extraordinary magnetic field, roughly 1 trillion times stronger than Earth's, and roughly 10 billion times stronger than the strongest magnet in any laboratory. But a pulsar's magnetic field, powerful as it is, pales in comparison to the magnetic field of a magnetar. A magnetar's field is roughly 1,000 times stronger than a typical pulsar's, roughly 10 to the 15th Gauss, 1 quadrillion Gauss. It is this factor of 1,000, this leap from the already extreme to the truly incomprehensible, that transforms a neutron star from a pulsar into something far more dramatic, far more dangerous, and far more scientifically fascinating. But how does this happen? How does a neutron star, born in the chaos of a supernova explosion, acquire a magnetic field 1,000 times stronger than its siblings? What makes one neutron star a pulsar and another a magnetar? The answer lies in the first few seconds after the supernova, in the turbulent, convective, unimaginably violent conditions inside the newly born neutron star. And that is where we turn next, to the moment of birth, the first heartbeats of a magnetar, the few seconds that determine whether a neutron star will live out its days as an ordinary pulsar, or will become the most powerfully magnetized object in the universe. Section 3. Born in Fire and Magnetism. The birth of a magnetar is not a separate event from the birth of a neutron star. Every magnetar begins as a neutron star, forged in the same cataclysmic supernova explosion we described in the previous section. The difference lies not in the birth itself, but in the conditions during the first few seconds of the neutron star's existence. A brief, critical window during which the neutron star's magnetic field is either amplified to extraordinary levels or settles into the more modest values typical of ordinary pulsars. The fate of the neutron star, whether it becomes a magnetar or a pulsar, is determined in roughly 10 to 30 seconds. 10 to 30 seconds out of a lifetime that will span millions or even billions of years. It is one of the most consequential brief periods in all of astrophysics, and understanding it requires us to delve into the physics of dynamos, dy nu schmos, convection, and the behavior of conducting fluids under extreme conditions. Let us begin with a question that might seem simple but is actually profound. Where do magnetic fields come from? In everyday life, we encounter magnetic fields in permanent magnets, in electromagnets, in the magnetic field of the Earth itself. But what generates these fields? The answer, in almost every case, is the motion of electrically charged material. A magnetic field is produced whenever electric charges move. An electric current flowing through a wire generates a magnetic field around the wire. Molten iron circulating in the Earth's outer core, driven by convection and the rotation of the Earth, generates the geomagnetic field that protects our planet. The motion of charged plasma inside the Sun generates the solar magnetic field, with its complex structure of sunspots, coronal loops, and magnetic cycles. In every case, the fundamental principle is the same. Moving charges create magnetic fields. This is one of the cornerstones of electromagnetism, codified in Maxwell's equations in the 1860s, and it is the key to understanding how magnetars acquire their extraordinary fields. The process by which the motion of conducting fluid generates and sustains a magnetic field is called a dynamo, dy-neuchmo. A dynamo is not a simple intuitive concept. It requires the right combination of fluid flow, electrical conductivity, and geometry to work. Not every moving fluid generates a magnetic field. The flow must be turbulent and three-dimensional. It must involve both differential rotation and convection, and the fluid must be electrically conductive enough that the magnetic field, once generated, is effectively frozen into the fluid, carried along with it, twisted and amplified by its motion. In the interior of a newly born neutron star, all of these conditions are met, and met to an extraordinary degree. When the core of a massive star collapses to form a neutron star, the result is not a calm, settled, static object. The newly born neutron star, sometimes called a protoneutron, proh-neutron star, is a seething, turbulent, fantastically energetic ball of matter. Its interior temperature is roughly 50 to 100 billion Kelvin, hot enough that the neutrons themselves are in a fluid state, not yet settled into the superfluid phase that characterizes older neutron stars. The neutrinos that are being produced in enormous quantities during the collapse are streaming outward through the neutron star, depositing energy as they go, driving violent convective motions in the interior. Convection, the rising of hot material and the sinking of cool material, is a familiar process. It happens in a pot of boiling water, in the Earth's mantle, in the outer layers of the Sun. But in a protoneutron star, convection happens at velocities and energy densities that are almost incomprehensible. The convective motions are turbulent, chaotic, and three-dimensional, exactly the kind of flow that can drive a dynamo. At the same time, the protoneutron star is rotating. Remember that the collapsing core conserved its angular momentum. A core that was rotating once every few seconds before collapse is now rotating many times per second. And here lies the critical factor that determines whether the dynamo will produce a Magnetar strength field or a more ordinary pulsar strength field. The key variable is the rotation period of the protoneutron star in the first few seconds after formation. The theoretical framework for understanding Magnetar formation through dynamo action was developed primarily by Robert Duncan, Duncan, of the University of Texas, and Christopher Thompson of the Canadian Institute for Theoretical Astrophysics, CITA. In a landmark pair of papers published in 1992 and 1993, Duncan and Thomson proposed that if a protoneutron star is rotating with a period of roughly 1 to 3 milliseconds, meaning it is completing between 300 and 1,000 rotations every second, the convective dynamo in its interior can amplify the magnetic field by a factor of roughly 1,000 compared to a more slowly rotating neutron star. The rapid rotation is crucial because it creates strong differential rotation, different layers of the neutron star rotating at slightly different rates, which stretches and amplifies the magnetic field lines. The combination of rapid rotation and vigorous neutrino-driven convection creates a dynamo of extraordinary efficiency, one that can generate magnetic fields of 10 to the 15th Gauss, or even higher in just a few seconds. Let us walk through this process step by step. The massive star has collapsed. The core has bounced. The supernova shock wave has been launched. At the center of the explosion, a protoneutron star sits roughly 50 kilometers across, still bloated and hot, gradually contracting toward its final size of 20 kilometers as it cools. In its interior, neutrino-driven convection is churning the neutron-rich fluid in great turbulent eddies. The protoneutron star is spinning very rapidly, with a period of perhaps 1 or 2 milliseconds. The convective eddies interact with the differential rotation, stretching magnetic field lines, twisting them, folding them back on themselves, amplifying the field with each convective turnover. The magnetic field grows exponentially, doubling and redoubling in strength with a time scale of roughly a few milliseconds. In 10 to 30 seconds, the field has been amplified from the initial seed field, perhaps 10 to the 12th gauss, to a final strength of 10 to the 15th gauss or more. The dynamo has done its work. Why must the rotation be so fast? Because the dynamo mechanism is essentially a competition between two processes. The convective motion amplifies the magnetic field by stretching and twisting field lines. But at the same time, the magnetic field tends to resist deformation and smooth itself out, a process called magnetic diffusion. For the dynamo to work, the amplification must happen faster than the diffusion. In a slowly rotating protoneutron star, the convective motions are not organized efficiently enough to outpace diffusion. The field grows, but only modestly, settling at the pulsar level value of 10 to the 12th gauss. In a rapidly rotating protoneutron star, the strong differential rotation creates large-scale, coherent flow patterns that amplify the field much more efficiently, overwhelming the diffusion and pushing the field to Magnetar level values. The threshold seems to be a rotation period of roughly 2 to 3 milliseconds. Below this period, the dynamo produces a magnetar. Above it, the result is an ordinary pulsar. There is an elegant analogy that can help us visualize this process. Imagine a pot of water on a stove. When the water is just warm, the convective motions are gentle and disorganized. Small eddies rising and sinking without any coherent pattern. But when the water is brought to a vigorous boil and you stir it rapidly with a spoon, the combination of the stirring, which represents the rotation, and the boiling, which represents the convection, creates organized, powerful flow patterns that are much more effective at mixing than the gentle, unstirred convection alone. In a protoneutron star, the rapid rotation is the stirring, the neutrino-driven convection is the boiling, and the magnetic field is what gets mixed and amplified. A slowly rotating protoneutron star is like a pot of gently simmering water, unstirred. The convection exists, but it is not organized efficiently. A rapidly rotating protoneutron star is like a pot at a furious boil, stirred vigorously from outside. The difference in the resulting magnetic field is not gradual. It is sudden and dramatic, a factor of 1,000 or more, the difference between a pulsar and a magnetar. It is also worth noting that the Duncan and Thomson model is not the only proposed mechanism for creating magnetar strength fields. An alternative hypothesis, sometimes called the fossil field hypothesis, suggests that some magnetars might inherit their strong fields from the progenitor star itself, if that star already possessed an unusually strong magnetic field. Certain massive stars, known as magnetic massive stars, or AP, AYP, and BP, BEEP stars, have surface magnetic fields thousands of times stronger than typical stars. If such a star collapses to form a neutron star, the conservation of magnetic flux during the collapse could amplify the already strong field to magnetar levels. The magnetic flux is proportional to the field strength times the cross-sectional area. When a stellar core millions of kilometers across collapses to a neutron star 20 kilometers across, the area decreases by a factor of roughly 10 to the 10th, and the field strength increases by the same factor. Starting from a surface field of a few thousand gauss on the progenitor star, this could yield a neutron star field of 10 to the 13 to 10 to the 14 gauss, approaching Magnetar strength. Whether this mechanism alone can produce the full 10 to the 15th gauss field, or whether a combination of fossil field and dynamo action is needed, remains an open question. The truth may be that both mechanisms contribute, with different magnetars forming through different pathways. This immediately explains why magnetars are rare. Not every massive star that explodes as a supernova produces a rapidly rotating core. In fact, most do not. The rotation rate of the core at the moment of collapse depends on the rotation rate of the progenitor star, the angular momentum transport within the star during its life, and the details of the collapse itself. Stars that have lost significant angular momentum through stellar winds, or that have experienced magnetic braking during their evolution, will produce slowly rotating cores and thus ordinary pulsars. Only those stars that retain enough angular momentum in their cores, or that experience conditions during collapse that spin the core up to the critical rate, will produce magnetars. The estimates suggest that roughly 10% of neutron stars become magnetars, perhaps 1 in every 10 supernova explosions. Given that supernovae occur in the Milky Way roughly once or twice per century, this means a new magnetar is born in our galaxy roughly once every few hundred years. Once the dynamo has amplified the magnetic field to its maximum strength, the field must be locked in. As the proto-neutron star cools over the next 10 to 100 seconds, its interior transitions from a hot, fluid state to a cooler, more ordered state. The outer layers solidify into a crystalline crust of iron group nuclei, a rigid lattice of atomic nuclei surrounded by a sea of electrons and permeated by the incredibly intense magnetic field. As the crust solidifies, the magnetic field is effectively frozen into the crust, locked in place by the high electrical conductivity of the neutron star material. The field can still evolve over time, and it does, as we will discuss in the final section, but the basic configuration, the 10 to the 15th Gauss Magnetar strength field, is established in those first few seconds and locked in by the solidification of the crust. There is a remarkable irony in the birth of a magnetar. The very thing that creates the magnetar, the rapid rotation, is also the thing that the magnetar most efficiently destroys. Once the magnetic field is established at 10 to the 15th Gauss, it acts as an extraordinarily powerful brake on the neutron star's rotation. The magnetic field extends far out into space, and, as the neutron star rotates, the field sweeps through the surrounding plasma and vacuum, radiating energy in the form of electromagnetic waves and accelerated particles. This radiation carries away rotational energy and angular momentum, slowing the neutron star down. The braking torque is proportional to the square of the magnetic field strength, so a magnetar, with a field 1,000 times stronger than a typical pulsar, experiences a braking torque roughly 1,000,000 times greater. As a result, magnetars spin down very quickly. A magnetar that was born spinning at a period of 1 or 2 milliseconds, hundreds of rotations per second, will slow to a period of several seconds within just a few thousand years. By contrast, a typical pulsar takes millions of years to spin down from a similar initial period. The magnetar's immense field is both its defining characteristic and the mechanism of its own deceleration, a cosmic paradox in which the most powerful magnet in the universe uses its own power to destroy the very rotation that created it. The result is an object unlike anything else in the universe. A sphere 20 kilometers across, spinning perhaps a few times per second, its initial extremely rapid rotation already significantly slowed by the enormous magnetic field, which acts as a brake, converting rotational energy into magnetic energy and radiation. The surface is a crystalline lattice of iron nuclei, unimaginably hard and rigid, the strongest solid material that can exist in nature. And threading through this surface, penetrating the crust, winding through the interior, and extending far out into the space surrounding the star, is a magnetic field of 10 to the 15th gauss, 1 quadrillion gauss, the most powerful magnetic field associated with any object in the known universe. The surface of a magnetar is a place of almost inconceivable strangeness. The magnetic field is so strong that it fundamentally alters the structure of matter. Normally, atoms are roughly spherical. An electron orbiting a nucleus occupies a cloud-like orbital that is, in most directions, roughly the same size. But in a magnetic field of 10 to the 15th gauss, the magnetic force on the electron is far stronger than the electrostatic force that binds it to the nucleus. The electron's motion perpendicular to the magnetic field is confined to an extremely small radius, while its motion along the field is relatively unaffected. The result is that atoms are no longer spherical. They are squeezed into long, thin, needle-like structures, elongated cylinders aligned with the magnetic field direction. The hydrogen atom, which in normal conditions has a diameter of roughly 1 angstrom, or 1/10,000,000th of a meter, becomes a cigar-shaped object hundreds of times longer than it is wide. This is not a small perturbation. It is a complete transformation of atomic structure, a revision of one of the most basic facts of chemistry, that atoms are round. In such a field, chemistry as we know it ceases to exist. The energy levels of atoms are completely rearranged. The familiar periodic table, with its patterns of chemical properties based on spherical electron orbitals, no longer applies. Molecules cannot form in their normal configurations. Materials behave in ways that no laboratory on Earth can replicate. The surface of a magnetar is, in a very real sense, a place where the rules of the familiar universe no longer apply, where matter itself has been reshaped by the overwhelming force of the magnetic field, and where the physics that governs everyday life gives way to something more extreme, more alien, and more beautiful. Let us consider, for a moment, the relationship between a magnetar and its immediate environment. The magnetic field does not stop at the surface. It extends far out into space, forming a structure called the magnetosphere, magnetosphere. A vast, complex arrangement of magnetic field lines that surrounds the star and shapes the behavior of any charged particles in its vicinity. In a pulsar, the magnetosphere is responsible for the emission of radio beams and other radiation. In a magnetar, the magnetosphere is even more active, crammed with magnetic energy that can be released in sudden, violent bursts. The magnetosphere of a magnetar is not empty space. It is a reservoir of energy, loaded and ready, like a spring compressed far beyond what seems safe, waiting for the trigger that will release it. And that trigger, as we shall see, comes from deep within the star itself. As the magnetic field evolves over time, placing enormous stresses on the crystalline crust, The crust eventually yields. It cracks. And when the crust of a magnetar cracks, the universe notices. But before we explore those violent outbursts, let us first understand the magnetic field itself in more detail. Let us understand just how powerful it is, what it does to the fabric of space, and why it makes a magnetar the most dangerous object you could encounter in the cosmos. That is the subject of our next section. Section 4. The Impossible Field. Let us now turn our attention to the magnetic field itself, this extraordinary, almost unbelievable force that defines a magnetar and sets it apart from every other object in the universe. We have mentioned the number already, 10 to the 15th Gauss, 1 quadrillion Gauss, and we have made some comparisons to familiar magnetic fields. But these comparisons, necessary as they are, barely scratch the surface of what it means for a magnetic field to be this powerful. In this section, we will explore the field in depth, examining its effects on matter, on light, on the vacuum of space, and on the laws of physics themselves. What we will discover is that a magnetar's magnetic field does not simply push and pull on things more strongly than other magnets. It changes the nature of reality around it. It enters a regime of physics where the ordinary laws that govern our everyday experience break down and must be replaced by something stranger, something that emerges from the deepest and most fundamental theories of physics we possess. Let us begin with the comparisons, because they are worth revisiting and expanding. The magnetic field of the Earth, the field that makes your compass point north, the field that shields us from the solar wind and makes the auroras dance above the poles, has a strength at the surface of roughly half a Gauss. This is the baseline, the familiar, the everyday. It is what we live in, what we evolved in, what our technology is designed for. Half a Gauss. A typical refrigerator magnet, the kind that holds a photograph or a grocery list to your refrigerator door, generates a magnetic field of roughly 100 Gauss, 200 times stronger than Earth's field. You can feel a refrigerator magnet. It pulls on other magnets, on iron, on steel. But it is, by the standards of human technology, a very weak magnet. You would not use a refrigerator magnet for any serious scientific or industrial purpose. A strong industrial magnet, the kind used in factories to lift cars or sort scrap metal, might generate a field of roughly 1,000 to 10,000 Gauss. At this strength, the field can exert significant forces on ferromagnetic materials. It can lift heavy objects, deform metal, and create hazards for anyone with metallic implants or pacemakers. A medical MRI machine generates a field of roughly 10,000 to 70,000 Gauss, with most clinical machines operating at roughly 30,000 Gauss, or 3 Tesla, Tesla, where 1 Tesla equals 10,000 Gauss. At this field strength, the machine can detect the faint magnetic signals emitted by hydrogen atoms in your body, using them to construct detailed images of your internal organs. But even at this relatively modest field strength, the safety precautions are extensive. Patients must remove all metal from their bodies. Ferromagnetic objects must be kept far from the machine. There are documented cases of oxygen tanks, wheelchairs, and other metal objects being pulled into MRI machines with lethal force. A gun was once pulled from a police officer's holster and into an MRI machine, discharging as it struck the magnet bore. At 30,000 Gauss, magnetic fields command respect. The strongest sustained magnetic field ever produced in a laboratory on Earth was generated at the National High Magnetic Field Laboratory in Tallahassee, Florida. using a combination of superconducting and resistive magnets. This field reached approximately 450,000 gauss, or 45 Tesla. Producing this field required enormous amounts of electrical power, sophisticated cooling systems, and a magnet that cost millions of dollars to build and maintain. At this field strength, the magnetic force on materials is immense. Small objects can be levitated, floating in midair in the intense field gradient. The field can affect chemical reactions, alter the properties of materials, and produce exotic quantum effects in certain types of matter. 450,000 Gauss represents, more or less, the limit of what human technology can achieve in a sustained, controlled manner. Now, a magnetar. A magnetar has a magnetic field of roughly 10 to the 15th Gauss. 1 quadrillion Gauss. Let us try to understand how this compares. The strongest laboratory magnet produces about 450,000 Gauss. A magnetar's field is roughly 2 billion times stronger than that. 2 billion times. If the strongest laboratory magnet were represented by a single grain of sand, the magnetar's field would be represented by a mountain. Not a small mountain. A mountain the size of Everest, multiplied several times over. The comparison simply breaks down. We are not talking about a difference of degree. We are talking about a difference so vast that it constitutes a difference of kind. To reach a magnetar's field strength starting from the Earth's field, you would need to multiply by a factor of roughly 2 quadrillion. If you doubled the strength of the Earth's magnetic field every second, starting now, it would take you roughly 50 seconds to reach the field strength of a magnetar. That might sound quick, but remember, doubling is exponential growth. After 10 seconds, you would be at roughly 500 Gauss, stronger than a refrigerator magnet. After 20 seconds, roughly 500,000 Gauss, comparable to the strongest laboratory magnets. After 30 seconds, roughly 500 million Gauss, stronger than any magnet humans have ever built. After 40 seconds, roughly 500 billion Gauss, comparable to the field of an ordinary neutron star. And after 50 seconds, roughly 500 trillion Gauss, approaching the field strength of a magnetar. Each doubling takes you into a new regime, a new realm of physics, and the final few doublings take you into territory where the laws of physics themselves begin to change. What happens to matter in a field this strong? We touched on this briefly in the previous section when we discussed the elongation of atoms. But let us explore this in more detail, because the effects are far more dramatic and far-reaching than simply changing the shape of atoms. At field strengths above roughly 10 to the 9th Gauss, or 1 billion Gauss, which is still a million times weaker than a magnetar's field, the magnetic force on an electron becomes comparable to the electrostatic force that binds the electron to its nucleus. This is the regime where atoms begin to deform. The circular orbits of electrons are squeezed into tight spirals aligned with the field, and the atom transitions from a three-dimensional sphere to a one-dimensional needle. But this is only the beginning. At field strengths above roughly 10 to the 12 Gauss, the characteristic field strength of an ordinary pulsar, the Landau quantization of electron orbits becomes important. In a strong magnetic field, electrons cannot orbit in any direction they choose. Their motion perpendicular to the field is quantized, restricted to discrete energy levels called Landau levels. In the ground state, the electron's motion perpendicular to the field is confined to a region comparable to the magnetic length, which at 10 to the 12 gauss is roughly 10 to the negative 11 centimeters, about 1/10 the size of a normal hydrogen atom. The atom is now a thin cylinder roughly 1/10 of an angstrom wide and a few angstroms long. It is still recognizable as an atom, but barely. At field strengths approaching 10 to the 15th gauss, the Magnetar regime, something even more fundamental changes. The energy associated with the magnetic field in a given volume of space becomes comparable to the energy associated with the mass of the particles in that volume, through Einstein's mass-energy equivalence. In technical terms, the magnetic energy density approaches the rest mass energy density of matter. This means the magnetic field is no longer a perturbation on matter. It is not simply pushing atoms around or deforming them. It is a fundamental ingredient of the physical system, as important as the matter itself. The field and the matter are intertwined, inseparable, each shaping the other in a mutual dance of quantum physics. In this regime, the vacuum of space itself is altered. This is one of the most remarkable and counterintuitive predictions of quantum electrodynamics, quantum electrodynamics, or QED, the quantum theory of light and electromagnetic interactions. In classical physics, the vacuum is nothing, empty space devoid of properties. But in quantum mechanics, the vacuum is not truly empty. It seethes with virtual particles, particle-antiparticle pairs that flicker into and out of existence for durations too short to measure directly. These virtual particles are not normally detectable, but in an extraordinarily strong magnetic field, they become important. The field interacts with the virtual electron-positron, POs IH-tron pairs in the vacuum, polarizing them, aligning them, changing the way the vacuum responds to electromagnetic radiation. The vacuum becomes birefringent, birefringent. Birefringence is a property more commonly associated with certain crystals, like calcite or Iceland spar. When light passes through a birefringent material, it splits into two beams that travel at slightly different speeds and refract at slightly different angles, because the material's optical properties depend on the direction of polarization of the light. The same thing happens in the vacuum near a magnetar. The intense magnetic field causes the vacuum to behave like a crystal, with different optical properties in different directions. Light, passing through the space near a magnetar, splits into two polarization modes, one with the electric field oscillating parallel to the magnetic field, and one with it oscillating perpendicular. These two modes travel at slightly different speeds through the vacuum, just as they would through a birefringent crystal. This phenomenon, called vacuum birefringence, was predicted theoretically in the 1930s, shortly after the development of quantum electrodynamics. Werner Heisenberg, H.Y. Zenberg, and Hans Heinrich Euler, I. Weiler, derived the effective theory describing how the vacuum responds to strong electromagnetic fields, and their equations predicted that the vacuum should become birefringent above a certain critical field strength. This critical field strength, called the Schwinger critical field, named after the American physicist Julian Schwinger, Schwinger, who contributed fundamentally to QED, is approximately 4.4 times 10 to the 13th Gauss. At this field strength, the energy stored in the magnetic field over a volume comparable to the Compton wavelength of the electron is equal to the rest mass energy of an electron. Above this critical field, the magnetic field can spontaneously produce real electron-positron pairs from the vacuum, converting magnetic energy directly into matter. A Magnetar's field, at 10 to the 15th Gauss, exceeds the Schwinger critical field by a factor of roughly 20. It is deep into the regime where quantum vacuum effects are not just theoretically predicted, but physically dominant. In 2016, a team of astronomers led by Roberto Mignani, Mignane, of the National Institute for Astrophysics in Milan, Italy, published a study that provided the first direct observational evidence for vacuum birefringence. Using the European Southern Observatory's Very Large Telescope in Chile, they observed a nearby isolated neutron star called RxJ, 185.6.5-3754, an object with a moderately strong magnetic field. By carefully measuring the polarization of the light coming from this neutron star, they detected a signal consistent with the vacuum birefringence predicted by QED. The result was not definitive, and further observations are needed, but it was a tantalizing hint that one of the most exotic predictions of quantum electrodynamics might actually be confirmed in the vicinity of strongly magnetized neutron stars. In the years since, additional observations with more sensitive instruments have continued to build the case. If confirmed beyond doubt, it would be one of the most remarkable experimental validations of quantum field theory, made possible not by any laboratory on Earth, but by the natural laboratory of a Magnetar's magnetic field. Let us now consider what would happen if a Magnetar were to appear somewhere much closer to Earth. This is a thought experiment, of course, not a realistic scenario, but it is useful for understanding the scale of the forces involved. Imagine that a Magnetar were to appear at the distance of the Moon, roughly 384,000 kilometers away. At that distance, the magnetic field of the Magnetar, which decreases with the cube of the distance for a dipole field, would still be extraordinarily strong. The exact field strength would depend on the orientation of the Magnetar's magnetic axis, but rough calculations suggest that the field at the distance of the Moon would be on the order of hundreds of Gauss to thousands of Gauss. That is still much stronger than any magnet in your home. At this field strength, the magnetic field would erase every credit card on Earth, every magnetic stripe on every card, in every wallet, in every purse. It would corrupt or destroy every magnetic storage device, every hard drive that relies on magnetic recording. It would disrupt every electronic device that uses magnetic components, which is to say, nearly every electronic device on the planet. Compasses would go haywire. Navigation systems would fail. The electrical grid would be severely disrupted as the changing magnetic field induced enormous currents in power lines and transformers. But the effects would go beyond technology. The human body contains iron. Not much, roughly 3 to 4 grams in the average adult, mostly in the hemoglobin, HeMo-GloH bin, of red blood cells, where it plays a critical role in transporting oxygen. In a magnetic field of thousands of Gauss, this iron would experience a noticeable magnetic force. It would not be ripped from your blood, not at the distance of the Moon, but the force would be detectable. Biological processes that depend on subtle magnetic interactions, such as the magnetic navigation used by birds and certain other animals, would be completely disrupted. Now, bring the magnetar closer. Imagine it at half the distance to the Moon, roughly 190,000 kilometers away. The magnetic field strength increases by a factor of roughly 8, because it follows the inverse cube law. Now, the field at the Earth's surface would be in the range of thousands to tens of thousands of Gauss, comparable to an MRI machine. At this distance, the iron in your blood would experience a significant magnetic force. Hemoglobin contains iron in a form that is not strongly ferromagnetic, which is why MRI machines are safe for humans. But in a field of tens of thousands of gauss applied over the entire body, the cumulative effects on blood flow and on the alignment of molecules would be substantial and dangerous. At a distance of roughly 10,000 kilometers from a magnetar, comparable to the diameter of the Earth itself, the field strength would be enormous, perhaps millions of gauss. At this distance, every atom in your body would be affected. The water molecules in your tissues, the proteins, the DNA, all of them contain electrons whose behavior is altered by the magnetic field. At millions of gauss, the molecular structure of biological matter begins to change. Chemical bonds are disrupted. Protein folding, the delicate three-dimensional shape that gives a protein its function, is altered. Enzyme function would cease. Your body, at a molecular level, would begin to disassemble. Not violently, not explosively, but systematically, as the magnetic field rearranged the energy levels of every electron in every atom, disrupting the chemical bonds that hold you together. Death would come not from impact, not from heat, not from radiation, but from the quiet, invisible rearrangement of your molecular structure by a force you could not see, could not feel in the ordinary sense, and could not resist. And if you were somehow transported to the surface of a magnetar, to that crystalline landscape of iron nuclei bathed in a field of 10 to the 15th gauss, you would not survive for even a fraction of a second. The magnetic field would compress every atom in your body into a needle-shaped cylinder, aligned with the field. Your molecules would be disassembled. Your atoms would be distorted beyond recognition. The field gradient, the rate at which the field changes with distance, would be so steep that the force on one side of your body would be radically different from the force on the other side, tearing you apart before the molecular disruption could even complete. Simultaneously, the immense gravitational field, 200 billion times the surface gravity of Earth, would compress you into a thin film of matter on the surface. The surface temperature, hundreds of thousands to millions of degrees, would vaporize whatever remained. There is perhaps no place in the universe where death would come in so many simultaneous forms, each one sufficient on its own, all of them arriving in the same instant. Yet for all its destructive power, the magnetic field of a magnetar is also a source of profound beauty and scientific wonder. The physics that governs the behavior of matter and light in these extreme fields is some of the deepest and most fundamental physics we know. The interaction between the Magnetar's field and the quantum vacuum tests the predictions of quantum electrodynamics in a regime that no earthly experiment can access. The deformation of atoms in the field probes the quantum mechanics of bound states under extreme conditions. The behavior of light near a magnetar, its splitting, its bending, its interaction with the magnetized vacuum, connects the physics of electromagnetism with the physics of quantum field theory in ways that illuminate both. Magnetars are, in a sense, natural laboratories for extreme physics, places where the universe has created conditions that push our theories to their limits and force us to confront the deepest questions about the nature of matter, energy, and space. We cannot build a 10 to the 15th Gauss magnet in any laboratory on Earth. We cannot even come close. But nature has built them for us, scattered them across the galaxy, and equipped them with phenomena that radiate signals we can detect from thousands of light years away. All we have to do is look and listen and try to understand. And one of the most dramatic ways in which magnetars make themselves known, one of the most violent and spectacular phenomena associated with any object in the universe, is through the starquakes and giant flares that erupt from their surfaces when the immense stresses of the magnetic field become too much for the crystalline crust to bear. These events, brief and blinding, are what we will explore next. Section 5. Starquakes and Giant Flares. Magnetars are not quiet objects. They do not simply sit in space, spinning silently, their immense magnetic fields reaching out into the void like invisible arms. They are, on the contrary, among the most violently active objects in the known universe. They tremble, they crack, they erupt. They release bursts of energy so intense that they can be detected across the entire galaxy and beyond. Bursts so powerful that a single event, lasting less than a second, can release more energy than our sun produces in hundreds of thousands of years. The story of Magnetar outbursts is a story of unimaginable violence locked inside a tiny, dense sphere. A story of forces in conflict, of structure under stress, of a magnetic field so powerful that the very crust of the star cannot contain it. It is one of the most dramatic chapters in all of astrophysics, and it begins with a crack. To understand Magnetar outbursts, we must first understand the two observational classes through which magnetars were originally discovered. Classes that were recognized as distinct phenomena long before they were unified under the Magnetar model. The first class is called soft gamma repeaters, or SGRs, and the second is called anomalous X-ray pulsars, or AXPAs. The story of how these two classes were discovered, studied, and eventually understood to be the same type of object, magnetars, is one of the great detective stories of modern astrophysics. Soft gamma repeaters were discovered in the late 1970s and early 1980s, when a series of gamma-ray detectors aboard satellites began detecting brief, intense bursts of soft gamma rays, meaning gamma rays at the lower energy end of the gamma-ray spectrum, coming from fixed positions in the sky. Unlike the classical gamma-ray bursts that were being studied at the time, which appeared at random positions and never repeated, these sources emitted bursts repeatedly from the same location. They would be quiet for weeks or months, and then suddenly release a burst of gamma rays lasting a fraction of a second, followed by more bursts over the next few hours or days before falling silent again. The bursts were short, typically a tenth of a second to a few seconds, and their energy spectrum was softer, meaning lower energy, than classical gamma-ray bursts. The first such source was identified in 1979, and by the late 1980s, several SGRs were known. Anomalous X-ray pulsars were discovered around the same time, but through a different channel. These were neutron stars detected as sources of pulsed X-ray emission, similar to ordinary X-ray pulsars, but they were anomalous in a critical way. Ordinary X-ray pulsars are powered by accretion, the transfer of material from a companion star onto the neutron star. The infalling material releases gravitational energy as X-rays, and the rotation of the neutron star causes the X-ray emission to pulse. But the anomalous X-ray pulsars had no companion stars. They were isolated. There was no accretion, no infalling material, nothing obvious to power the X-ray emission. And yet they were emitting X-rays at a luminosity far greater than could be explained by the rotational energy of the neutron star alone, which is what powers ordinary radio pulsars. something else was providing the energy. The AXPs were spinning down, losing rotational energy, but the rate of spin down was too slow to account for the observed X-ray luminosity. They were, in a word, anomalous. The resolution of both puzzles came from the Magnetar model proposed by Duncan and Thomson. They realized that both SGRs and AXPs could be explained as neutron stars with ultra-strong magnetic fields, Magnetars. The energy source was not rotation, as in pulsars, and not accretion, as in X-ray binaries, but the magnetic field itself. The enormous energy stored in a 10 to the 15th Gauss magnetic field is more than sufficient to power the observed X-ray emission of AXPs and the gamma-ray bursts of SGRs. The field decays over time, converting magnetic energy into heat and radiation, and it is this magnetic energy that lights up the magnetar. The SGR bursts occur when the stresses imposed by the evolving magnetic field cause the crust to fracture, releasing stored magnetic energy in sudden, explosive events. The AXP X-ray emission is powered by the steady dissipation of magnetic energy in the interior and the surface of the star. Two classes of objects. One explanation: Magnetars. Let us now delve into the mechanism of starquakes, the fractures that produce the violent outbursts of SGRs. The crust of a neutron star, as we discussed earlier, is a crystalline lattice of iron group nuclei, extraordinarily rigid and strong. The breaking strain of a neutron star crust, the amount of stress it can withstand before fracturing, is estimated to be roughly 10 to the minus 1, or about 10%. This is enormously high compared to any material on Earth. The breaking strain of steel is roughly 10 to the minus 3, or about 1/10 of 1%. Neutron star crust is roughly 100 times stronger than steel in this regard. And yet, even this extraordinary strength is not enough to resist the forces imposed by a magnetar's magnetic field. The magnetic field of a magnetar exerts forces on the crust because the field lines are anchored in the crust, threading through it, and any change in the configuration of the field creates stresses on the lattice. As the magnetic field evolves over time, driven by processes in the interior such as ambipolar, ambi-POHLR, diffusion, and Hall drift, the field lines shift and twist. These shifts pull on the crust, trying to reshape it, trying to move the crust to accommodate the new field configuration. The crust resists, and stress builds up. It is exactly analogous to the tectonic stresses that build up along earthquake faults on Earth, where two plates push against each other until the rock can no longer withstand the force and suddenly slips. In a magnetar, the plates are replaced by the crystalline lattice, and the tectonic forces are replaced by magnetic forces. But the principle is the same. Stress builds. The crust holds. Stress increases. The crust still holds. And then, suddenly, catastrophically, the crust yields. It fractures. A starquake. A Magnetar starquake is not like an earthquake. It is vastly more energetic, even relative to the size of the object. When the crust of a magnetar fractures, the stored magnetic energy is released in a burst. The energy propagates outward through the magnetosphere as a wave of magnetic field reconfiguration, a process analogous to a magnetic reconnection event in the Sun's corona, but far more extreme. Charged particles are accelerated to relativistic velocities, approaching the speed of light. Photons are produced across a wide range of energies, from radio waves to X-rays to gamma rays. The event is visible across interstellar distances, and, in the case of the most extreme events, across intergalactic distances. The energy released in a typical Magnetar burst, the kind detected routinely from SGRs, is roughly 10 to the 39th to 10 to the 41st ergs. For comparison, the total energy output of the Sun in 1 second is roughly 4 times 10 to the 33 ergs. A typical Magnetar burst releases roughly 1,000,000 to 100,000,000 times the Sun's energy output per second, all in a flash lasting a fraction of a second. These are the routine events, the background level of Magnetar activity, the cosmic equivalent of minor tremors. They are interesting, they are energetic, they are far beyond anything we experience on Earth, but they are not what makes magnetars famous. What makes magnetars famous is what happens when the fracture is not minor but massive, when the stored energy is not gradually released but catastrophically dumped in a single, blinding event. A giant flare. There have been 3 confirmed Magnetar giant flares observed in the era of modern astronomy, and each one has left an indelible mark on the field of high-energy astrophysics. The first was the event of March 5, 1979, one of the most remarkable and consequential observations in the history of gamma-ray astronomy. On that date, a burst of gamma rays struck the Earth that was so intense it saturated the detectors aboard multiple spacecraft, overwhelming instruments that had been designed to measure the most energetic events in the universe. The burst came from the direction of the Large Magellanic Cloud, a satellite galaxy of the Milky Way located roughly 160,000 light-years from Earth. The source was later identified as SGR 0526-66, a soft gamma repeater in the supernova remnant N49. The burst arrived with a rise time of less than a millisecond, an almost instantaneous onset that indicated an explosion of extraordinary violence. The initial spike lasted roughly 0.2 of a second and released an energy of approximately 10 to the 44 ergs. After the initial spike, the emission settled into a decaying tail that lasted several minutes, and this tail displayed a remarkable property. It pulsated. The emission rose and fell with a period of roughly 8 seconds, matching the rotation period of the neutron star. This pulsation told astronomers that the emission was coming from a localized region on the surface of a rotating object, and the 8-second period was consistent with the spin of a neutron star. The March 5 event was the first observational evidence for a new class of astrophysical phenomenon, though it would take more than a decade for the full Magnetar interpretation to be developed. The second confirmed giant flare occurred on August 27, 1998, from SGR 1900+14, a magnetar located roughly 20,000 light-years away in our own Milky Way galaxy. This event was detected by multiple satellites and ground-based observatories, and it provided a wealth of data that confirmed and extended the Magnetar model. The initial spike of the 1998 event was even more energetic than the 1979 event, and the pulsating tail was observed in exquisite detail, revealing complex structure that provided information about the magnetic field geometry and the physical processes occurring on the surface and in the magnetosphere of the Magnetar. But it was the third event, the giant flare of December 27, 2004, that truly stunned the astrophysical community and brought Magnetars to the attention of the broader scientific world and the general public. On that date, a Magnetar designated SGR 1806-20, located roughly 50,000 light-years away on the far side of the Milky Way galaxy, unleashed the most powerful flash of energy ever detected from beyond our solar system by any instrument in human history. The event was so energetic, so far beyond anything previously observed, that it rewrote the record books and forced a reassessment of the maximum energy that a magnetar can release. The initial spike of the December 27 event lasted approximately 0.2 of a second. In that 0.2 of a second, SGR 1806-20 released an energy of approximately 10 to the 46 ergs. Let us put this number in context. The total energy output of the Sun is roughly 4 times 10 to the 33 ergs per second. In 1 year, the Sun produces roughly 1.2 times 10 to the 41 ergs. In 250,000 years, the Sun produces roughly 3 times 10 to the 46 ergs. A magnetar released that much energy in 0.2 of a second. 250,000 years of solar output, compressed into a time interval shorter than the blink of an eye. The gamma-ray pulse from this event was so intense that it affected the Earth's atmosphere, despite the fact that the magnetar was 50,000 light-years away, on the other side of the galaxy. The pulse ionized the upper atmosphere, the ionosphere, ionosphere, on the daytime side of the Earth, producing a measurable increase in the electron density at altitudes of 20 to 60 kilometers. This ionization was detected by instruments that monitor very low-frequency radio propagation, which is sensitive to changes in the lower ionosphere. A star 50,000 light-years away, so far that its light takes 50,000 years to reach us, briefly altered the chemistry of our atmosphere. From that distance, the magnetar was approximately as bright as the full moon in gamma rays for a fraction of a second, except that the energy was in gamma rays rather than visible light, and gamma rays carry millions of times more energy per photon. The pulsating tail of the December 27 event lasted approximately 400 seconds, or nearly 7 minutes, and displayed a pulsation period of 7.56 seconds, the spin period of SGR 1806-20. The tail emission was complex and evolving, with the pulse profile changing over time as the trapped fireball of radiation and plasma that was confined by the magnetar's magnetic field gradually cooled and shrank. The total energy in the pulsating tail was roughly 10 to the 44 ergs, 100 times less than the initial spike, but still enormous by any standard. Detailed analysis of the tail emission provided constraints on the magnetic field, strength, the size and temperature of the emitting region, and the physical processes responsible for confining the radiation. The December 27 event had several important scientific consequences. First, it confirmed that magnetars can store and release truly stupendous amounts of energy, far more than what the routine SGR bursts had suggested. The energy of the giant flare was comparable to the total magnetic energy stored in the magnetar's field, suggesting that the event involved a global restructuring of the magnetic field, not just a local fracture. The entire crust may have shifted and fractured, releasing a significant fraction of the total stored magnetic energy in a single catastrophic event. Second, the event raised the terrifying question of what would happen if such a flare occurred from a magnetar much closer to Earth. SGR 1806-20 is 50,000 light-years away. The nearest known magnetar to Earth is roughly 10,000 light-years away. But magnetars are difficult to detect when they are quiescent, and there may be magnetars much closer that we have not yet identified. If a giant flare of the magnitude of the December 27 event occurred from a magnetar at a distance of, say, 10 light-years, the consequences for Earth would be severe. The gamma-ray flux at Earth's surface would be enormous, roughly 10 to the 38 ergs at 10 light-years compared to 10 to the 46 ergs at the source. The ozone layer would be partially destroyed by the high-energy radiation, increasing the flux of ultraviolet light from the sun reaching the surface. The disruption to the ozone layer could persist for years, potentially causing widespread ecological damage. Some researchers have speculated that a Magnetar giant flare within 10 light-years of Earth could trigger a mass extinction event comparable to the major extinction events in the geological record. Whether any of the known mass extinctions were actually caused by such events remains an open and fascinating question. Third, the December 27 event, along with the earlier giant flares, led to a productive new line of research connecting magnetars to extragalactic transients. If a giant flare can be detected from 50,000 light-years, the distance of SGR 1806-20, then a similar flare from a magnetar in a nearby galaxy at a distance of a few million light-years would also be detectable, though much fainter. And, indeed, astronomers have identified several short-duration gamma-ray transients in nearby galaxies that are consistent with Magnetar giant flares. These extragalactic Magnetar flare candidates were initially classified as short gamma-ray bursts, a class of events traditionally attributed to the merger of two neutron stars. The realization that some apparent short gamma-ray bursts might actually be Magnetar giant flares seen at extragalactic distances has important implications for our understanding of both magnetars and the gamma-ray burst population. Before we leave the topic of magnetar outbursts, let us discuss one more connection, one that represents one of the most exciting developments in magnetar science in recent years: the link between magnetars and fast radio bursts, or FRBs. Fast radio bursts were discovered in 2007 by Duncan Lorimer, Lorimer, and his colleagues, who found a bright, millisecond duration pulse of radio emission in archival data from the Parkes Radio Telescope in Australia. The burst was extraordinarily bright, suggesting an origin at cosmological distances, billions of light-years away, and its brief duration indicated an emission region no more than a few hundred kilometers across, small enough to be consistent with a neutron star. In the years that followed, more FRBs were discovered, and the field exploded. By the early 2020s, hundreds of FRBs had been detected, some of which repeated, emitting multiple bursts from the same source over periods of weeks, months, or years. The repeating FRBs were particularly tantalizing because they implied a source that survived the emission of each burst and could produce more, unlike a catastrophic event like a supernova or a neutron star merger that destroys the source. The connection between magnetars and FRBs was dramatically confirmed on April 28, 2020, when a burst of radio emission was detected from a magnetar in our own galaxy, SGR 1935 plus 2154, located roughly 30,000 light-years away in the constellation Vulpecula. The burst, designated FRB 200-428, was detected by the Canadian Hydrogen Intensity Mapping Experiment, known as CHIME, and the Survey for Transient Astronomical Radio Emission 2, known as STARE-2. It was accompanied by a simultaneous X-ray burst from the same magnetar, providing the first unambiguous association between a magnetar and a fast radio burst. The radio burst from SGR 1935 plus 2154 was roughly 1,000 times less luminous than the faintest extragalactic FRBs, raising questions about whether the Milky Way magnetar was simply a weaker version of the same phenomenon, or whether the extragalactic FRBs are produced by more extreme events or by magnetars with even stronger magnetic fields. These questions remain open and are the subject of intense, ongoing research. But the basic connection is clear. Magnetars can produce radio bursts that share at least some of the properties of the mysterious FRBs, and magnetars are likely responsible for at least some fraction of the FRB population. It is a beautiful convergence. Two of the most puzzling phenomena in modern astrophysics, magnetars and FRBs, turning out to be related different facets of the same underlying physics. The study of magnetar outbursts, from routine SGR bursts to the spectacular giant flares to the connection with FRBs, reveals magnetars as objects of extraordinary violence and energy. They are not static. They are not calm. They are compressed reservoirs of magnetic energy, slowly releasing that energy through a combination of steady emission and sudden, explosive events that rank among the most powerful in the universe. But this violence cannot last forever. The magnetic energy is finite, and as it is dissipated, the magnetar grows quieter, calmer, less terrifying. Over thousands of years, the fire dies down, the tremors cease, and the magnetar fades into the vast population of ordinary, quiet neutron stars that drift through the galaxy. It is to this twilight phase, the ending of the magnetar's story, that we now turn. Section 6. A Brief and Brilliant Life. Everything ends, even magnetars. Even the most powerful magnets in the universe, the most violent, the most terrifying, the most extreme objects that nature has produced, they too have a finite lifetime, a beginning and an end. A brief and brilliant story that is told in a cosmic language of magnetic fields and gamma rays and starquakes, and then, slowly, gradually, inevitably, falls silent. A magnetar's magnetic field, the 10 to the 15th Gauss engine that drives all of its extraordinary behavior, decays. It does not last forever. The processes that sustain the field, the currents flowing in the crust and the interior of the neutron star, gradually dissipate. The energy stored in the magnetic field is converted into heat and radiation, warming the neutron star's surface, powering the X-ray emission that we observe, and slowly, inexorably, reducing the field strength. The time scale for this decay is roughly 10,000 years. It is not precisely known, and different theoretical models give somewhat different estimates, ranging from a few thousand years to perhaps 30,000 years. But the order of magnitude is clear. On a time scale of roughly 10,000 years, the magnetic field of a magnetar decays from 10 to the 15th Gauss to roughly 10 to the 12 or 10 to the 13 Gauss, the level of an ordinary pulsar. 10,000 years. In human terms, that is a vast span of time. It encompasses the entire history of civilization, from the first cities of Mesopotamia to the present day. In the lifetime of a human being, 10,000 years is roughly 130 generations. But in cosmic terms, 10,000 years is nothing. The universe is 13.8 billion years old. A magnetar's active lifetime of 10,000 years is to the age of the universe as a single second is to roughly 435,000 years. It is less than a heartbeat, less than a blink, less than the flutter of an eyelash. The most powerful magnets in the universe exist for a cosmic eye blink, and then they are gone. As the magnetic field decays, the magnetar's behavior changes. The SGR bursts become less frequent and less energetic. The X-ray luminosity decreases. The spin-down rate slows because the magnetic field is responsible for the braking torque that slows the neutron star's rotation, and as the field weakens, the torque diminishes. The starquakes become less frequent because the evolving magnetic field places less stress on the crust. The giant flares, the spectacular events that can be detected from across the galaxy, become rarer and eventually cease altogether. The magnetar grows quiet. Eventually, after roughly 10,000 to 30,000 years of active life, the magnetar has exhausted its magnetic energy. The field has decayed to the level of an ordinary pulsar. The exotic phenomena that defined the magnetar, the starquakes, the gamma ray, bursts, the X-ray emission powered by magnetic dissipation, the distortion of atoms and the birefringence of the vacuum, all of these fade away. What remains is a neutron star, still dense, still compact, still spinning, still possessing a magnetic field far stronger than any magnet on Earth, but no longer extraordinary by the standards of neutron stars. It is an ordinary pulsar, or perhaps an ordinary isolated neutron star, slowly cooling, slowly spinning down, drifting through the galaxy as a quiet, unremarkable relic of its former glory. The magnetar is dead. Long live the neutron star. How many dead magnetars are there in the Milky Way? This is a fascinating question, and the answer is staggering. Magnetars are born roughly once every few hundred years in the Milky Way, and the galaxy is roughly 13 billion years old. Even accounting for the fact that the rate of star formation and supernova production has varied over the history of the galaxy, a reasonable estimate is that roughly 30 million magnetars have been born over the galaxy's lifetime. 30 million. Each one burned brightly for a few thousand years, flaring and shaking and terrifying any observer who happened to be looking, and then faded into silence. Each one left behind a quiet neutron star, still drifting, still spinning, still out there somewhere in the dark. 30 million dead magnetars, scattered throughout the Milky Way, ancient remnants of brief, brilliant lives, now indistinguishable from the general population of old neutron stars unless we happen to find some subtle signature of their former glory. And yet, despite the millions of magnetars that have lived and died in the Milky Way, we have only identified roughly 30 that are currently active. 30. In the entire observable Milky Way, with its hundreds of billions of stars and its vast spiral arms, and its teeming stellar nurseries and ancient globular clusters, we know of roughly 30 magnetars that are currently in their active phase, currently exhibiting the extreme magnetic behavior that defines them. This is partly because magnetars are intrinsically rare, born only in a small fraction of supernova explosions. It is partly because their active lifetime is so short, just 10,000 years out of a galaxy that is over 13 billion years old. And it is partly because they are difficult to detect, their emission being primarily in X-rays and gamma rays, wavelengths that require space-based observatories to observe. The known magnetars are almost certainly just the tip of the iceberg. There are probably many more active magnetars in the galaxy that we have not yet detected, hidden behind clouds of gas and dust, or in regions of the sky that our telescopes have not surveyed with sufficient sensitivity. The current census of known magnetars includes objects in a variety of states. Some are actively bursting, producing regular SGR-like bursts and occasionally larger flares. Others are relatively quiescent, emitting steady X-ray radiation but showing no recent burst activity. Some have been detected as transient sources, briefly flaring into activity after years or decades of silence, and then fading again. A few have been identified through their association with supernova remnants, the expanding shells of gas produced by the supernova explosions that created them, which provides an independent estimate of their age. The youngest known magnetar, associated with the supernova remnant Kesteven 79, is estimated to be roughly 400 years old, a newborn by cosmic standards. The oldest active magnetars are perhaps 10 to 20,000 years old, approaching the end of their active phase. There is something poignant, something almost melancholic about the brevity of a magnetar's life. Here is an object that possesses the most powerful magnetic field in the universe, a field that can distort atoms, bend light, crack its own surface, and ionize the atmosphere of a planet 50,000 light-years away. And yet, on the timescale of the cosmos, its existence is fleeting, almost ephemeral. It blazes for a cosmic instant and then fades, leaving behind only a quiet neutron star and, perhaps, the slowly dissipating remnants of its supernova. The universe does not seem to care about the brief magnificence of a magnetar any more than it cares about the brief magnificence of a firefly. Both burn. Both fade. Both leave the universe slightly different than they found it, and both are forgotten in the vast indifference of time. And yet, we care, we notice, we study and wonder and try to understand. From our small planet, orbiting our ordinary star, in our unremarkable spiral arm of the Milky Way, we have reached out with our instruments and our mathematics and our imagination and touched these objects, these distant, terrifying, beautiful things. We have detected their flares from across the galaxy. We have measured their spin, periods, to extraordinary precision. We have modeled their interiors using the deepest theories of physics we possess. We have predicted their existence before we observed them, and we have confirmed those predictions with observations that validated our understanding of nature at its most extreme. The study of magnetars is one of humanity's great intellectual achievements, a triumph of curiosity and persistence and the stubborn refusal to accept that the universe is too vast or too extreme or too strange to be understood. Let us think for a moment about the nearest known magnetar to Earth. It is SGR 1627-41, located roughly 10,000 light-years away. At that distance, even a giant flare would produce no measurable effect on Earth. We are safe. The nearest known magnetar is too far away to harm us, too far away to disrupt our technology, too far away to pose any threat to life on our planet. But it is close enough to study, close enough to observe, close enough to learn from. And there may be magnetars closer that we have not yet found, quiet ones, dead ones, or perhaps a young one lurking behind a cloud of dust in a part of the sky we have not yet surveyed with the right instruments. The galaxy is vast, and our knowledge of it is still incomplete. But tonight, let us not worry about that. Tonight, let us simply rest with the knowledge of what we have learned, and let it settle into that quiet place where understanding and wonder meet. We have traveled together through the life and death of a magnetar, from the explosive birth of a massive star to its catastrophic death in a supernova, from the dynamo that amplifies the magnetic field in the first few seconds of a neutron star's existence to the extraordinary properties of the field itself, from the starquakes and giant flares that make magnetars the most violent transient objects in the galaxy, to the slow, gentle decay that eventually returns them to silence. You have learned that magnetars are neutron stars, roughly 20 kilometers across, with magnetic fields of roughly 10 to the 15th gauss. You have learned that these fields are roughly 1 quadrillion times stronger than the Earth's magnetic field, strong enough to distort atoms, split light, alter the vacuum of space, and kill from distances measured in astronomical units. You have learned that magnetars are born in the supernova explosions of massive stars, in a brief window of dynamo activity lasting just 10 to 30 seconds. You have learned that they shake and crack and flare, producing some of the most energetic events in the universe. And you have learned that they are temporary, their extraordinary fields decaying over roughly 10,000 years, leaving behind quiet neutron stars that drift through the galaxy for billions of years, carrying no memory of the fire they once contained. There are, perhaps, 30 million dead magnetars in the Milky Way right now, and there are, perhaps, 30 that are still alive, still burning, still terrifying, still beautiful. Somewhere in the galaxy, at this very moment, a magnetar is spinning in the dark, its tremendous field reaching out across the void, its crystalline crust straining under magnetic stresses that will one day cause it to crack. Somewhere, a starquake is building, a fracture waiting to happen, a burst of gamma rays preparing to race across the galaxy at the speed of light. And somewhere, in a supernova remnant still glowing faintly with the heat of an explosion that happened a few hundred years ago, a newborn magnetar is settling into its existence, its dynamo freshly wound, its field freshly frozen into its crust, its brief and brilliant life just beginning. You do not need to think about them any longer. You do not need to hold the numbers in your mind, the quadrillions and the billions and the 10 to the 15ths. You do not need to picture the fractured crusts and the giant flares and the needled atoms and the birefringent vacuum. All of that can wait. It will all be here tomorrow, unchanging, patient, eternal on the time scale of your life. The magnetars will still be spinning. The neutron stars will still be drifting. The universe will still be vast and strange and more beautiful than any mind can fully grasp. For now, all that matters is this: you are here, you are warm, you are safe. The nearest magnetar is 10,000 light-years away, and the gentle magnetic field of the Earth is wrapped around you like a shield, as it has been wrapped around every living thing on this planet for billions of years. Half a gauss, that is all that touches you. Half a gauss, just enough to guide a compass needle, just enough to steer a migrating bird, just enough to remind you that the universe is built on forces both grand and subtle, both terrifying and gentle. The room around you is quiet. The world outside is quiet. The stars above you, if you could see them through the ceiling, are quiet too, burning steadily, fusing their hydrogen, spinning their slow and patient rotations, sending their light across the void to arrive here, at this moment, at this place where you are resting. Among those stars, hidden in the darkness between them, the magnetars spin their faster, fiercer rotations, but their fury is far away and cannot reach you. You are held by gravity and shielded by a magnetic field, and surrounded by an atmosphere, and warmed by a star that has 5 billion years of steady burning still ahead of it. You are, in every sense that matters, safe. Let your breathing slow. Let your thoughts become soft and formless. Let the magnetars and the neutron stars and the supernovae and the iron cores and the crystalline crusts all blur together into a gentle haze of wonder, a quiet amazement that will follow you into sleep and perhaps, if you are fortunate, into your dreams. You have traveled far tonight, across the galaxy and into the hearts of the most extreme objects in the universe. You have looked at things that no human eye can see, touched ideas that no human hand can grasp, and felt, even if only through the medium of words and imagination, the sheer, overwhelming power of a magnetar's magnetic field. And now it is time to rest. The universe has shown you some of its secrets tonight, and it will show you more tomorrow if you come back. There are always more secrets. There are always more wonders. The cosmos is inexhaustible, and so is the human desire to understand it. But understanding can wait. Tonight, all that matters is the softness of your pillow, the weight of your blanket, the quiet rhythm of your breathing, and the knowledge that somewhere out there, in the great dark spaces between the stars, the Magnetars are spinning, their tremendous fields sculpting the space around them in invisible patterns of unimaginable beauty. And you are drifting, slowly and gently, into a peaceful and dreamless sleep. Good night.